prefer to stand down here if you don't mind, and use my laser pointer from time to time maybe. This project is actually part of the WUNA project, and I'm glad that Max Weckermann repeated again what Kai presented in the morning. He gave an overview about this huge project funded by the Gates Foundation. So, as Max mentioned, it's about collecting the urine from the UD toilets and making a fertilizer out of it. And my part is about the network management. So basically, you've seen these pictures before. So in this project, as well as in previous projects, we did a lot of effort on developing technologies on producing a good fertilizer out of urine. There's also a lot of work going on the UD toilet side, but what is very important part is the missing link. It's not the missing link, it's the link between. We actually have to be sure that we get the urine from the toilets to the treatment site. Without this transport, the whole system won't work. This is how it's currently done here in Durban for the feeding of the reactors Max was talking about. It works, it's expensive, it's not yet optimized. That's clear of all of us, but it really works. It can be quite complex, the whole system, with people dropping off the urine to a community center, and then it's collected maybe in several stages to a treatment site. It can also be that a treatment is locally and then the product is collected. So there's many different options to look at if you want to understand and optimize this system. So that's why we decided to make a model. But very quickly, let me give you some points. I thought about why am I presenting this at Faecal Sludge Management Conference. But during the last 1.5 days, you already heard a lot about urine treatment, so it definitely fits very well into this conference. And there's, of course, many things in common between urine collection and treatment and fecal sludge management. One thing is that the collection itself is crucial for both. You have to get the stuff out of the toilets to a central or decentralized location to be treated. And it's expensive, this collection. We're talking about a large number of toilets to be serviced. There's many different collection schemes are possible, and different business models and stakeholder interests, so it's not just possible to analyze it in 5 minutes on a small piece of paper. And if you go the way for urine diverting toilet, as they are at least partly doing it in Durban here, we have to manage the fecal sludge and the urine, because we have two product streams in the end. Okay, let's go back to the system, and to some questions I think they're important to answer when it comes to collection of these products. How much urine is available for treatment plant? If you think about the treatment plant at the site some of you may visit tomorrow, how much can we get there? Not only how much, but also how reliable will it arrive there? And how expensive it is to get this amount there. So, with the model, we can then also ask questions: what are the most important factors we really have to look at and really have to get the data, and which factors are negligible? And this applies for many different contexts or questions. So, is it about the volume delivered, the reliability? Is it about the costs? Which factors are important for the costs? For the profit of a small entrepreneur doing this collection? For environmental pollution? There's many different aspects of looking at this whole collection issue. So now, to the model. We developed the model to answer such kind of questions. The goal of this model is to understand or to facilitate the understanding of the system. That's why we went for a mechanistic model that actually these parameters, they mean something to the user. Moreover, the processes behind, particularly the human behavior and the human metabolism, is stochastic. It's not every day the same. Not every person produces every day the same amount of urine with the same concentration of nitrogen, phosphorus, whatever. The same applies for pit toilets. I had some interesting discussion this week that it's highly variable, the filling rate of a pit. So that's why this model also is stochastic. That means if you run it twice with the same parameters, we'll get two different results. And basically we want a flexible model, a modular model that we can analyze many different schemes and contexts. How shall we do that, or how did we do it? Looking at this drawing here I made, it's getting obvious that the whole collection system is actually a series of tanks. There's tanks in the toilets, there's tanks being transported, there's tanks sitting in different parts in the city as well as in front of the treatment. And they're filling up, they're emptying, there's reactions going on in these tanks. So that's the basic of the model, which we call DSAM for Decentralized Sanitation Product Management Model. So I just want to introduce you quickly to the basic elements. They're very simple, and with these different collection schemes can be modeled. The basic element is tank, as I mentioned before. There's influent, effluent, an overflow, and there's something that controls the effluent. It's not a technical controller, it can be a pump, by the way, but it can also be a collection team that drives around with a pickup truck and collects the stuff, or it can be people dropping off the urine at the neighborhood center. These are all processes that control how much goes actually out of the tank. If there's too much flowing in and too little flowing out, then we'll have overflow. There's information exchange, for example, how much people drop off depends definitely on how much is actually in the tank. So far, I implemented 3 different options for these effluent controllers: pumps or pipes, pickup, and drop-off, the 3 options I just mentioned. Then there's a wastewater generation element, the households, and in this house there's also let's call it overflow to the environment. This is the fraction of urine that doesn't end in the toilet. And this is a very big issue, discussion and research topic in this WULA project, because a large percentage of the excreted urine doesn't end up in the toilet for various reasons. That people go to work, to the city, or that they pee into the bush. And then there's sink elements, just to mathematically collect all the results to do some statistics in here. Additionally to the volume flow, the model can deal with mass transfers. So, of course, the urine volume flow does contain compounds, whatever compounds we define in the beginning. But then there can be additional reactions like volatilization to the air of nitrogen, or precipitation of strurite in the tanks, and so on. And the actual treatment plants can be eventually modeled as well, but it's not yet implemented. So this DSAM is a modular flexible system. So for this kind of system, we can just put all these different elements together and let it run. And all of these elements can actually have many parallel sub-elements. Let's say this household is actually 500 households of one area that share the same characteristics of urine production and toilet use. And then the mass transfer reactions can be added as well. So the model calculates first the volume flows through the whole thing, and then adds the mass flows, and in the end adds the cost. I want to show you this simple example, just a few parameters to show you the abstraction level of the parameters, and then some results. So we have some households here with different ways the urine can be lost, because people are not at home, people don't use the toilet at home, or technical issues like wrong pipe connections. Then it goes through the toilet. There's these tanks at the toilets, collection with a pickup truck to a buffer tank in front of the treatment. So now comes a slide to the stochastics. I think Kai Uda showed it already or he did actually show it already in the morning session. In all the households, there's different number of people living, and these excrete a different amount of urine every day. So what the program does, it takes random numbers out of this probability density function and creates a new distribution of how much urine is produced per household and day. This is here, the input to the whole system. And then there's a certain probability that people actually use the toilet. So this is done with this, can be any probability function that goes between 0 and 100% of any shape can be used to decide how much of this urine of each household each day ends actually up in the toilet. And you see in the end that this distribution is much closer to 0 than the excreted one. The real data are actually much closer to 0 than what I showed here. Let me show you some parameters for the collection. One important parameter there is the number of tanks one team can empty per day, and then the number of teams that are running in parallel. So this involves a lot of other factors that are not modeled, like distance to drive, topography, ease of access, idle time, other things that these teams do on the way. This is information the local users have to gather and put into the model. This, on the other hand, makes the model broadly applicable to many different contexts without actually trying to model the driving times and walking times to all these houses. Another thing is the collection order. So there's basically two options. These teams, they can go from house to house following a list, and the next day they continue the list from where they stopped the day before, or they can always go to the fullest tank. Let's say they can do 50 tanks a day. That's a typical number here in Durban at the moment. And if there's 1,000 households in the area, they can always go to the 50 fullest tanks, which is much more efficient, of course. How can they know which tanks are the fullest? One option is to install online sensors. That may be not appropriate in the areas we're working in Durban, but maybe for other contexts. Another option may be applicable for fecal sludge management. People can call, hey, listen, my tank is full, or my pit is full, please come as soon as possible. Or just by experience of the workers, that they know which tanks are typically full first. This is a very cheap option then, of course, maybe as good as the online sensors. If we talk about dropping off the urine at the households, they bring the urine and get some, like a list tilly presented in the morning, maybe even get some money or some other things as incentive to bring the urine. In the model, it's implemented as a probability that they drop off the urine today. And that depends on the volume, but there's, again, it's very flexible. Any empirical function can be added. Now let me show you some results, and I'll show you the results of what's coming into the buffer tank in front of the treatment, like what's delivered from the collection. 500 households, we get a certain amount of urine excreted, and a fraction of it ends actually in the toilet. I'll show you the values per week, because if you talk about 5 working days or 7 working days a week, that may cause a bit of confusion on if you talk about liters per day. So these values are liters per week for the 500 households. Then this green bar, that's the amount that's collected, that ends in the buffer tank, and the rest that's overflowing in all these 500 toilet tanks. This is for 20 liter tanks, 5 days collection a week, and for this fixed collection order that the team just followed the list. Now let's have more teams running in parallel every day, and so we end up with less overflow and more collected, but of course that adds to the cost. I'll show that in a minute. Now these are the same numbers. I just show them as points that I can add some more lines. Let's have them work 7 days a week. Then we can collect more, there's less overflow. Or bigger tanks, 40 liter tanks. Or this optimized collection route that they always go to the 50 fullest tanks, so then we highly reduce the overflow, but we still have some overflow. Now, these are average values over 3 years, these 500 households. No, first the cost, sorry. Now, let's change to the cost in the x-axis. These are US dollars per week, including the installation of the tanks at the toilet, not the toilet itself, but the tanks at the toilet and the operation of the collection and the buffer tank. So we see that the option with the 7 days, that was the red one, it's actually more expensive than the other options because we have to pay salaries for 7 days. We can also look at the specific costs, US dollar per liter in this case. So we can play around with different options, many more of course, and look at volumes, at costs we have to pay, at total cost, at specific costs, whatever, you name it. And now, as I mentioned before, these are average numbers. So what's behind this value, for example, this is a distribution of all the values behind this over 3 years. Daily values actually multiplied by 7 to fit into this scale. So you see, this is the mean value, but most values are somewhere up here, and there's a lot of zero values as well. So this information is all in the results of the model and can be analyzed, and some statistics can be done to understand what's happening. So let me explain you what's behind this with some another view to the data. These are some of these 500 households, the average over time, but for each individual household. So we see that the actual excretion, these are the gray bars, is highly different among the households, and the yellow bars, that's what's ending up in the toilet. Again, it's highly variable and not necessarily, not much to do, doesn't correlate with the length of the gray bar. Now the green is what's collected, and the red is the overflow. So you see clearly that there's a certain capacity of this collection scheme that's implemented. This is with this fixed collection order. Now look at these household tanks over day. This is over the days, 3 weeks, the average of all these tanks. So because this collection is happening only 5 days a week, that's just an assumption I made in the model, there's a clear weekly pattern of the collection, no collection on the weekend, and because of that, there's also a weekly pattern of the overflow in the sum of all these tanks. And this is actually what's delivered to the tank in the end. So this is why there were so many zero values and variation among the others. Now let's go further down to the buffer tank. The buffer tank in this example has a certain volume. This amount is delivered every day or every working day, and then there's a pump that runs continuously feeds the nitrification plant, let's assume Max talked about, and as he mentioned, nitrification reactor needs continuous feed. So that's what we want. But we see that actually this tank runs empty. This is just the level in the tank, the gray bars here. It runs empty at the weekends, actually Sunday and Monday, until Monday evening the next delivery comes. So this is not what we want for the treatment plant. How can we improve the whole thing? Let's first improve the collection by always collecting the fullest tanks. So we highly reduce the overflow. Also here, it's visible that the overflows at the toilet is highly reduced. That means we actually deliver more, collect and deliver more urine to the buffer tank. But we can still not eliminate these empty periods after the weekend, but we create a lot of overflow at this buffer tank, which is maybe better because maybe this site is connected to a sewer, whatever, but we don't want to lose all these volumes. What can we do? Let's build a smaller plant there. Maybe we just over-design this plant. So if you have a smaller pump at least, then we can continuously feed the reactor, but then we just lose more in the overflow. Or another option, just have a bigger tank there, so that we have much more buffer volume, so that we have less overflow and actually can allow a continuous feed. So this dynamic and stochastic data allow actually to go into the detail and understand what's going on in this system, and to really understand the numbers and how the things can be fixed. Let me summarize. Collection is crucial for treatment of human waste, decentralized human waste, and for nutrient recovery. Main question, how much urine or nutrients can we get for what cost? With what reliability? The model is thought to support the understanding of the system behavior, therefore it's mechanistic, stochastic, and dynamic. The design model is a modular model. It can model very different schemes, layouts. It can model volume flows, mass flows, and costs. And as you've seen with the abstraction level of all these parameters, there's many more parameters, of course. Local knowledge is definitely needed to apply it to a certain question, and the user has to be intelligent. So to really understand how to relate the real world to the model and then back to the real world. And this makes the model widely applicable, and I personally also think that this prevents a lot of misuse or abuse of such models. Quick outlook, in the further time of the WUNA project, the model will be applied to the Durban situation. We also are continuously gathering more data to calibrate the model for the situation we have here. The model will be used as a tool for the development of a business model, again for this urine and possibly even fecal sludge management systems. So this model can then play or give results to certain collection schemes to evaluate their business models. And further model development will take place, mainly to incorporate more reactions like different treatment technologies. Thank you for your attention.